Student friends, today I will going to be discussing about introduction to IR spectroscopy. Do you know what's meant by IR spectroscopy? IR is nothing but the electromagnetic radiations. By using these electromagnetic radiations, that is infrared, we analyze organic compounds. Particularly, we are going to be detecting the functional groups present in the organic molecules. So infrared spectroscopy, that is this particular spectroscopy is going to be fall under the absorption spectroscopy, and here the molecules are going to be absorbing this particular IR radiations and going to be excited, and they will give some different kind of spectra like rotational spectra and vibrational spectra and so far. So let us know before that what is exact IR range. Here three sections are there for this IR radiation. First is near IR, middle one is normal IR, and third is far IR. And you have here values mentioned below to this particular range, that is 12,500 per centimeter to 4,000, that is for near IR. Then 4,000 to 667 per centimeter, that is for normal IR, and then for far IR, that is 667 to 50 centimeter. So out of these three ranges, this is the middle one, that is normal IR, having frequency 4000 to 667 is diagnostic for our organic molecules, and that is the required one. So before that, you must know some different terms involved in this particular spectroscopy. That is, the first one is to be called molecular vibrations. So I am already told you during this particular spectroscopy, some different vibrations, that is rotational spectra and vibrational spectra are obtained, and that is what very important for this molecule, for this particular spectroscopy. So let us see what is molecular vibrations. Here, molecule is not a rigid assembly of atoms. Instead of that, the atoms in a molecule vibrate, as a result of which bond length may change. Means whatever bond length is there in the molecule, that may decrease or increase. Okay, or bond angle may also going to be changed, that also going to be decrease or increase. The molecule can exist in different vibrational levels which are quantized. When infrared radiation falls on the sample, here sample is nothing but the organic molecule, the molecule undergoes specific vibrational transitions, that is V0 to V1, and energy is going to be absorbed, which results in the appearance of an absorption band in the spectrum. So you can see here, this is a schematic vibrational and rotational energy levels, and these changes are occur whenever the organic molecules are going to be absorbing IR radiations, and such type of vibrational transitions and rotational changes are to be occur. So before that, you must know the some fundamental terms involved in this particular molecular vibrations. So here two terms we are going to be defining. The first is to be called here stretching vibrations, and second is bending vibrations. So let us see first of all what are the stretching vibrations. So during these particular vibrations, two types of stretchings are occur. First, that is symmetric stretching, and second, that is asymmetric stretching. So you see, in case of symmetric stretching, so whenever the central atom is going to be joined by means of different atoms, and during this stretching, the bond present in between the two atoms may be stretched or may be compressed, just like a spring. So whenever both atoms are going to be stretched away from the central atom, then that stretching is to be called symmetric stretching. In second case, in case of asymmetric, what happens? In case of one bond, it's going to be compressed to the central atom, and one going to be stretched out of the central atom. And if this type of stretching occurs, then it should be called or referred as a asymmetric stretching. And normally, whenever this kind of stretchings are occur, asymmetric stretching frequencies are always going to be more than that of the symmetrical stretchings. Let us go for second vibration that is called bending or deformation vibration. Normally bending and deformation vibrations has require less frequency as compared to the stretching vibrations. So in this case there are four different stretchings are going to occur. Two of them are going to be in plane vibrations and two of them are going to be out of plane vibrations. So see, first and second, that's called scissoring and rocking. These two vibrations are occur in a plane, whereas the twisting and wagging, two others, those are to be occur in out of plane. So in case of scissoring and rocking, you can see here in the figure, in first figure in scissoring, both the bonds moves just opposite directions. One goes to right side, another goes to left side. In second one, in case of rocking, both the bonds moves to one side, either left or either right. Then this type of vibrations are referred as scissoring and rocking, and both are going to be takes place in a plane. Whereas the remaining two, that is twisting and wagging, these two are out of plane vibrations. So here twisting is going to be occur. So one bond is to be positive, another is going to be negative. Or right side going to be positive and left is going to be negative. Or both may be positive, both may be negative. So these are going to be just vibration takes place out of plane. Next very important point is that what are the conditions for absorption of IR radiations. So if you want to analyze the organic compound, your compound must be having dipole moment. That is the required condition. Because if the compound which do not have dipole moment, they are not going to be absorbing IR radiations. Ultimately they are not going to be producing the spectra. So that is the one of the required conditions for this IR spectroscopy. So you can see here, vibrational frequency of the molecule must be same as the frequency of infrared radiations. That is the first condition. And I am just already told you that second condition, there must be change in dipole moment of the molecule as a result of vibrations. You can see here two examples. One is going to be carbon double bond oxygen. So this is a polar bond because carbon is linked with oxygen, carbon having positive charge and oxygen having negative charge. So this is to be polar, and this particular group is going to be active. And in second case, carbon double bond carbon. So this is non-polar because both the carbon atoms are same electronegativity. So here carbon double bond having no dipole moment, whereas carbon double bond oxygen having a dipole moment. So before that, one more very important concept that you should know, that is what to be called as number of fundamental vibrational modes. So this should be considered in degrees of freedoms. So what is meant by degrees of freedom? So you know an atom has 3 degrees of freedom with respect to 3 Cartesian axes, you know, x, y and z. Okay. Thus the molecule with n atoms will have 3n degrees of freedom because of 3 Cartesian axes. The 3n degrees of freedom of the molecule will be made up of rotational, vibrational and translational degrees of freedom. So this point is to be considered for 2 types of molecules in our compound. That is one for non-linear molecule and second is to be for linear molecule. So let us study about the non-linear molecule. So here you see here in non-linear molecule, it has 3n minus 6 fundamental vibrations, out of which n minus 1 are stretching and 2n minus 5 are bending vibration. For example, you can see here the one example, that is methane CH4. It has, you know, n equal to 5 because total atoms for this particular CH4 molecules are 5. So 3 into 5 minus 6 equal to 9 vibrational modes. So out of which 4 are stretching and 5 are bending vibrations. So how we are getting this particular stretching and bending vibrations? You have formula n minus 1. So n minus 1 is nothing but 5 minus 1 goes to 4, and 2n minus 5 you also put here value 5. So it should be 5 are bending vibrations for non-linear molecule, that is a CH4. So similarly you can go for linear molecule. So in case of linear molecule, fundamental modes of vibrations is nothing but 3n minus 5. So for example, you can consider here CO2 example, carbon dioxide. So it has 3 total number of atoms. So 3 into 3 minus 5 equal to 4 vibrational modes of vibrations, out of which 2 are stretching and 2 are bending vibrations. Similarly, you can go for diatomic unsymmetrical molecules like HCl, HF have 1 vibration mode, but symmetrical molecules like H2, oxygen, nitrogen, Cl2 molecule, Br2 molecule do not absorb. This is because absorption cannot occur if the vibration is electrically symmetrical. That's the important criteria for the IR spectroscopy. So see, the next point is very important for this spectroscopic technique, that is IR spectroscopy, that is calculation of vibrational frequencies, or it should be called position absorption band. So it is very important to calculate frequencies for the typical bond. So for this purpose, there is one formula, and that is what to be as a nu bar equal to 1 upon 2 pi c under root k upon mu m. So where you can see here, nu bar is the vibrational frequency measured in centimeter inverse. C is the velocity of light, that is a constant. K is a force constant of the bond. So this is very important point again. K is the force constant for respective particular bond, and mu is nothing but to be called reduced mass. So here Ma into Mb divided by Ma plus Mb, where Ma and Mb are the masses of bonded atoms A and B. Suppose CX bond is there, so mass of carbon and mass of X. So that is the example. So this is the formula. On the basis of this, you can calculate how this particular frequency is going to be correlated with the force constant, again correlated with the reduced mass. So you can see in the formula, so frequency is directly proportional to the square root of force constant and inversely proportional to the reduced mass. So suppose if force constant increase, ultimately frequency is going to be increase, and if reduced mass increase, frequency decrease, because they are inversely proportional. So this relation is very important while comparing the frequencies for different type of function group present in the molecule. Okay, or some factors also going to be affecting the frequencies for the typical function groups, either electron donating, withdrawing, or some other kinds of effects are also going to be happens. So during that case, you can explain how frequency is decreasing or increasing for that particular respective functional group or particular bond. So here this is to be referred as a Hooke's law. So this Hooke's law is going to be defining very proper frequency for the functional group or particular bond. So here I have given some examples how the frequency is going to be decreasing or increasing for different particular compound. So you can have here if Ma and Mb remains the same. Ma and Mb is nothing but the mass of A atom and mass of B atom. Here the larger the value of K, the higher will be the vibrational frequency, because the force constant K run parallel to bond strength. So here it's very important that force constant is going to be simply parallel to the strength of the bond. Means what only here? More the strength of the bond, ultimately more the force constant. So that point is going to be considered here, and you can have here 3 different type of bonds are given: carbon-carbon triple bond, then double bond, and then single bond. And observed frequencies values are also mentioned over here. For triple bond it should be 2100 per centimeter value. For double bond it should be 1650, and for single bond it should be 1000 per centimeter. So why the values are decreasing from first to last? So you can think over here that here carbon-carbon triple bond has more strength. It is more tighten the bond. So whatever strength of the bond is there, that is more in case of triple bond than the rest of the two, and so far the frequency for the triple bond is more than that of the double bond, and consequently than the single bond. This kind of things you can observe. So in second case, what we have done, if K remains constant, K means force constant remains constant, and then we increase Mb then Ma. So Ma keeping constant here. So Ma is nothing but the carbon in these two examples, and Mb is nothing but the, in one case, hydrogen, and in second case, deuterium. Then we expect that the frequency is to be decreased. Why it is so happens? In case of CH, so carbon is same for both these cases, but in both these cases, second atom, in one case it is hydrogen and in second case it is a deuterium. So deuterium have more mass as compared to hydrogen, and frequency is going to be inversely proportional to the reduced mass. So if mass of the atom increases, so ultimately frequency decreases, and that's why in case of CH it is to be observed at 2000 to 3100, and for CD bond it should be observed at 2200. You can also see such kind of effect, how frequency decreases in the order. So you can take one example, CH, then carbon-carbon, then CN, and then CO bond. So what happens here? The first one you can observe here 2900 to 2800, in second 1680 to 1620, 1220 to 1020, and last one is 1050. Here what happens? What is the reason here? You can think over here, mass is going to be increased. First carbon remains constant, but second atom is going to be constantly changed. Hydrogen, then carbon, then nitrogen, then oxygen. So what happens here? Mass of this second atom is going to be increased, and due to increase in the mass, frequency is going to be reducing, and that you can observe from the first to last. Again, you can observe similar kind of effect in case of CF, CCl, CBr, and Ci. So if you are coming from left to right, the second atom, mass of the second atom is continuously increased, and so the frequency also going to be continuously decreased from left to right. And all these examples you can explain on the basis of Hooke's law. You can see in the third example, third case, if K and MA and MB are different, then we expect that frequency to increase with increasing value of K. So here it is very important. Here in all these three cases, the CH bond is keeping constant. Means carbon is everywhere, carbon is same, everywhere hydrogen is same. But whatever carbon is there, that linking to other carbon is in different way. In first case, it is going to be joined with triple bond. In second case, it is connected with double bond. And in third case, it is connected with single bond. So you can observe here the hybridization of carbon. In first case, it is sp. In case of 2, it is second case, it is sp2, and in case of third, it is sp3. So what happens here? As the sp, you know already that sp is more electronegative than the sp2, and sp2 is more electronegative than sp3, and that's why whatever CH bond frequency is there, that is going to be, yes, it is more force constant this CH bond has than this CH in case of second, than the CH in case of third, and that's why values also you can observe for first is more and for second is somewhat less, and again it is less in case of the third one. Yeah, so again we are going to be explaining in this some different phenomena which increase the number of absorption band, and there are some different phenomena also decrease the number of absorption bands. So this is to be what called as the overtones or harmonics. How it is to be observed? So it is observed for some molecules. So overtone bands appear at integer multiples of the fundamental vibrations. And why these are occurs? You just see here, these are occurs due to the V0 to V2 transition instead of V0 to V1. So normally we expect that normal transition, that is V0 to V1. But sometimes what happens, so different kind of transition, direct V0 to V2 takes place, and due to this some overtone bands or harmonics are going to be observed. So you can see one example here, the strong absorption at 1710 per centimeter of acetone will give rise to weaker absorption band at 3420 per centimeter, and this is the 3420 per centimeter value is the band that is the due to the, yes, overtone. Second is combination tones. So this may also possible that maybe one frequency is combined with another frequency values. So two frequencies here may interact to give a new absorption bands which are combination or difference frequencies. That's why some combination tones are going to be also observed. So here suppose first one is X and second is Y. So X plus Y may take place or X minus Y also may take place. So this kind of tones are to be referred as a combination tones. So third one is also there, that is what to be called Fermi Resonance. So here, when fundamental vibration may couple with overtone or combination tone, so here it is very important, fundamental vibrations are coupled with overtone or with combination tone of some other vibration, then it is called as Fermi Resonance, and this is to be referred as a Enrico Fermi, who first discovered it, and that's why it is referred as a Fermi Resonance. These are the different phenomena which normally reduce the number of absorption bands. Earlier phenomena which are going to increase the number of absorption bands. So how they reduce? You see here, fundamental frequencies that fall outside the normal IR region. Sometimes what happens, some fundamental frequencies, they are just come out of the IR regions. Automatically they are going to be reducing. They are not going to be observed. One more, fundamental bands that are too weak to be observed. In some cases, some bands are going to be there, but they are indicating very weak, what I am saying, that the spectra, signals. And third is there, fundamental vibrations that are so close that they coalesce. That means they are merging, okay, in one in another. They are merging, and that's why again it should be reducing. Fourth one, occurrence of generate band from several absorption of same frequency. And number fifth one is certain fundamental vibration fail to appear in IR because of lack of required change in dipole moment of molecule. I am already told you, so it is very important to analyze the organic molecule. So whatever molecule you are going to be consider for the analysis, that compound must have a dipole moment, then that will give the absorption bands in proper region. If the compound have no dipole moment or less dipole moment, they are not going to be showing their proper fundamental vibrations because of this reason. So these are the references for this particular IR spectroscopy introduction and basic principle for the technique. Thank you.